Hello and welcome to our discussion and demonstrations of how to identify minerals and demonstration of mineral properties. We'll start out first by defining what a mineral is, and then we'll systematically walk through each of the mineral properties that you'll need to use to describe and then eventually come up with a mineral name for your Lab 1 and Lab 2 assignments. The definition of a mineral has 5 components. The first is a mineral must be naturally occurring. It cannot be man-made or synthetic. Now, if a mineral occurs in nature, such as ruby or a diamond, both of those are possible, could possibly be synthesized by man and are. We call them mineraloids. So technically, not strictly minerals if they've been made by man. However, their natural counterparts are. Inorganic minerals inorganic is by definition needed for mineral. Now, this is complicated by the fact that some minerals are made in nature by biological organisms, such as algae or worms or other types of organisms, clams, oysters that live in marine environments. Traditionally, though, we don't see a lot of carbon-hydrogen bonds that we might expect in organic compounds like benzene or methane. So the carbon, hydrogen, and oxygen that occur in many organic molecules and compounds these elements are going to show up in our body. They're also going to show up in minerals, but they're not going to be bonded together or with the same mineral structure. The mineral must be solid. It has a well-defined crystalline structure. This means that we know how all the atoms are bonded to one another and where they exist in three-dimensional space. And finally, we have to have a well-known chemical formula. This doesn't mean that every mineral is pure. There are many kinds of minerals. Many of them have imperfections and impurities, trace elements in them that don't really allow for the mineral formula to be perfect. And commonly, for instance, we make some assumptions about what a mineral is made out of when we're in the field, and then we take it to the lab to identify precisely what's in it, so we can know what those impurities are. Okay? As far as properties go, here's a list of the main properties I'll talk about and either demonstrate briefly using a document camera. So I'll flip out of this or switch out of this PowerPoint and then switch over to another instrument so I can demonstrate to you what's going on. Color, luster, hardness, cleavage, habit form, streak, striations, magnetism, reactivity, and specific gravity. These are the common features that we're going to be using, or common properties, and the ones that you'll want to know, and they'll be very useful for getting us to a mineral name. Color is fairly straightforward. It is not diagnostic in the sense that color doesn't define what a mineral is, but it does help to pare down. If you have a group of 20 minerals, it could get you to 10 as potential options, or get you to 7. Both minerals here are SiO2. The one on the left you may have seen before. It's purple quartz, which is also called amethyst. On the right, quartz is translucent, and you can see some interesting grooves on the surface of this particular mineral. I'll come back to this a little bit later. You can see these grooves here, here, also there at the top. Those are called striations, and I'll define what those are a little bit later. Luster refers to the reactivity of, the way in which a mineral reacts with light near it or at its surface. And for our purposes, we're interested in those classifying minerals in 2 schemes. One is metallic, and the other is non-metallic. Non-metallic has a number of classifications within it, including vitreous, resinous, greasy, pearly, silky, and adamantine. The most common of these non-metallic will be vitreous, and sometimes we call that glassy. So I'd like to demonstrate a little bit by showing you what metallic and non-metallic look like here. If I just pop out of this and pop into my document camera. Let's first look at metallic minerals. Metallic minerals are highly reflective. Okay? In this case, you have a kind of golden color that you can see, a brassy golden color. Tend to be opaque and tend to be made of have colors that are gold or silver in nature, brass, maybe even yellow. Okay, I can bring out yet another metallic luster here. Notice the golden color and how highly reflective it is. Okay? Let's compare this to something that is non-metallic, okay, and clearly glassy, right? A light color, pink in this case. This is a glassy type mineral. Now there are some minerals that you may not necessarily know if they're glassy or not. Here's a mineral that I would say is glassy, okay, but dark in color, almost black. So it is reflective, but it doesn't look like metal. Okay? So for our purposes, it's either metallic or non-metallic. I will bring out one mineral that is commonly defined as pearly. That is this mineral here. Sometimes you'll get it to have a kind of iridescence. You can see it is reflective there. And that iridescence, the pinks, the blues that you get from, let's say, a pearl or an opal, those are what we're looking for. This mineral is not exhibiting that very well, but it is, or it does have what we consider to be a pearly luster. Pop back over to the PowerPoint here. And here are some examples of luster. One that I did not show you is here, but you'll be able to sort of figure this out as you're looking at the minerals. This guy on the right, top right, is dull or earthy. So it's still a non-metallic classification, but it is, you'll have at least one or two minerals that fall into that kind of characteristic, and they'll look distinctive. Okay? The next property is hardness. Hardness is defined on a relative scale from 1 to 10, so there are no units involved. And the Mohs scale was developed by Moh, a person, for a group or a set of minerals. So we have some of these minerals in our kit here, and I'll just point out the ones we have. We have quartz, orthoclase, fluorite, calcite, gypsum, and talc. But you don't need all of these minerals to use Mohs scale and to use it as in a testing kind of evaluative fashion. The only thing we need really is our fingernail and a steel, or I'm sorry, not a steel file. Let me back up, a piece of window glass. Here it is, a piece of window glass. The window glass comes in at about 5.5 on Mohs scale, close to 6, and your fingernail is about 2.5. So what this means is if you scratch the mineral with your fingernail and it scratches, then the mineral is softer than 2.5. Okay? Now, if you don't scratch the mineral with your fingernail, it means it's harder than your fingernail, and you need to go to another test. That test is with window glass. If the same mineral that you couldn't scratch with your fingernail also cannot scratch glass, that means you're now between 2.5 and 5.5, and you've figured out what the hardness is. Alternatively, the mineral that you're testing then scratches glass, leaves a mark on the plate, and is harder than 5.5. Those three groups, less than 2.5, 2.5 to 5.5, and greater than 5.5 are all you need to identify the mineral. So don't worry when you may read that there's a mineral that has a hardness of like fluorite, which is 4.2 or 4.3. These things are things we can determine, but they're not particularly useful for working through all of the minerals. I back out of this particular show and head to our document camera. I'll try and demonstrate what's going on here. So the fingernail part is very easy to work with. I'll put this mineral here. And this is the mineral calcite, and we'll see if I can scratch it with my fingernail or make a mark on it. And as you can see, I didn't really make a mark on it. It's a non-metallic mineral, and there's nothing there that's really showing up. Let's pick another mineral to look at. Okay, here's a mineral. I'll try to scratch with my fingernail. And I'll try that one more time. A little hard for you to see, but it did scratch a little bit. I can scratch this particular mineral with my fingernail. So this means that it's softer than my fingernail. It's less than 2.5. Compare it to this mineral, calcite, which I cannot scratch. This mineral is harder than 2.5. Bringing out my glass plate, which I have in my kit, I'm going to try and scratch the plate with the mineral. I find that it actually does not scratch, so there's no mark left here as I try to scratch it. So that means that calcite then is harder than 2.5, but softer than 5.5. The last version of this is for me to, of course, bring out something that's harder than 5.5. So I'll bring my streak plate out. I brought out this particular mineral, which is quartz, and I'm just going to scratch the tip right along the edge there, and we'll see if you can actually see it. It might be hard to see. Oh, you can kind of see that there's a little scratch right in here. Let me flip this around, and we'll just do one right across the middle here. Right here is where I made my next scratch, and you can see it there as I rotated in the light. See those little lines right there popping up right on top of my finger. Okay, so those are scratches that I just made. So your glass plate will have a mark. You don't need to pulverize the mineral or smash the glass plate. If the mineral is close to the hardness of the glass plate, it will leave a subtle scratch. However, if the mineral is much harder than the plate, it will scratch very easily, and you can see there are many, many deep scratches on this. Those are for minerals that are very, very hard. Okay. Garnet is close to about a 6 or 7, tends to scratch quite easily, and on Mohs scale, corundum is about a 9. And so we do have some of those in our lab. So P students have scratched the heck out of that little plate. Okay, so that was for hardness. The next property is called cleavage, and cleavage is a tricky one. It's one of the hardest properties. It takes the most practice to identify and to describe. It comes in multiple varieties, and it is the tendency by definition for a mineral to break along very straight fractures. Okay? We define cleavage in 2 ways. One is with the directions of cleavage. So that means then the unique spatial orientation. So if you've watched lecture on minerals, you know that minerals are made up of a lattice, and that lattice can have different kinds of bonds. And those bonds are arranged potentially in weak planes that can flake off or sheet off, creating layers or exposing layers of the mineral. But we also need to identify the number of directions, the number of unique spatial directions. So for our example here of muscovite, it's one direction, one perfect cleavage. And you can imagine that to be something like a ream of copy paper. If you were to pick up the paper after you've unwrapped it and looked at the side, you'd see many, many different layers. Each of those layers is the same direction. So that's what all these are, the same direction. Each layer that is parallel to the next layer is not a new direction. It's all part of the same spatial orientation. In some cases, we can add a second layer, and if I move down one, we've got one direction that's vertical and one that's horizontal in this case. And once we have more than one, we need to define the angle between those planes. In this case, the angle is at 90 degrees. Okay? In the next one down, we have 1, 2, and the third direction here is vertical. Okay? And the relationship among all those is at 90 as well. Okay? We can have 3 directions, which is the final one down here at the bottom, that are not at 90 degrees. So none of these are at 90 degrees. These angles are at something else. And so the key is to get the number of directions. And then we don't actually need to measure the cleavage angles for this particular class. So we can just say they're not at 90 or at 90. Okay, and that should be enough to get us to a mineral name. If we look at some examples of other things we might expect to see, when you're looking for cleavage, you're looking for flat surfaces. So all these minerals have flat surfaces. On the left-hand side, you can see the top surface is flat. You will also look for, and I'll just note these, flat surfaces. Okay. You're looking for parallel cracks. So there are hairline fractures that are very straight. Notice here is a hairline fracture. It's parallel to this fracture, which is parallel to this fracture, which is parallel to that fracture. Those are indicative of the presence of cleavage. Cleavage is not an irregular fracture. Okay, so we see straight, parallel cracks or fractures. Okay, so we have 1, 2 features. The next thing you can look for are stair steps, and we see examples of those here. Here is a little cleavage surface, and it steps up to this cleavage surface, which steps up to that cleavage surface. So that means that there's a direction of cleavage cutting through something like this. There are also stair steps here along this face as well, and then steps up, 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 up along that face in that case. So stair steps are good indicators of cleavage. The last one is sheets or layers. Okay, sheets or layers you can see in the center diagram here as this person's peeling off one of the layers of this muscovite. And I'll show you how to see that in minerals that have more than one direction of cleavage. Okay, so we'll back out of this for a second and flip over to our document camera. Let's just look at a simple one. So this is a mineral that we were just looking at in that diagram. If I flip it on its edge, you can see it's very thin. And if I even zoom in a little bit more here, it'll probably give us a little better view. That's about as close as I'm going to be able to get. But you can see the edge here. There's layers that are going to be able to be peeled off of this. And those layers, those lines, are our cleavage direction. So there's one perfect cleavage direction in this particular set. And like you can see, I'm almost peeling it apart right there. I don't want to break it. So that's cleavage peeling apart. That's one direction, okay? And there's no angular relationship for that. If you look at the surface of the mineral, I'll use my nail here. You can also see the sheets as they peel apart. You can see these probably easily here without getting it to reflect too much light at you. So you can see the sheet there. However, for some minerals, it's easier to see cleavage if it does reflect light back at you. So let's try another piece of a different mineral with multiple cleavages, and we'll sort of see if we can get it to reflect light, and then we'll see if that shows any sheets. We're looking at a cleavage surface. It's quite flat. Yes, okay, we're starting to get good reflection. So you want to hold it, and then you can see over here and over here, there's some little stair steps or sheets that you can see. So it's very small, these little steps. Those are indicative of a cleavage. Now, for most cleavage surfaces, we should be able to turn it over and find its mirror on the other side, which may also contain stair steps as well. Rotating it to get some reflection. We see a few in this sample. They're not excellent, I will say. Over here, you see one stair step or layer there. When you see these things up close, let me flip it over one more time. There will be some surfaces that are excellent at demonstrating this feature, and others that are not so good. There are some stair steps here to here, to here, okay? So you get some cleavage surfaces. You can see some of the layers, a few of the layers. I'll flip it over. Not a good surface on the other side. So this mineral does have two cleavage directions. Oh, the second one is here. Let's see if we can get it to reflect for us. Oh yeah, you can really see the stair steps here now. Here's a layer right here, here's a layer, and then here's another layer. Okay, so those are the sheets of the layers. This particular mineral I'm bringing out now is very good for demonstrating stair steps. You'll notice it's a metallic luster, and the steps are here to here, okay, to onto this other side here. So these are the stair steps here to here. It'll look like a series of cubes or lines that are passing through the mineral as well. Those are indicative of cleavage. They're very straight. They're all parallel. They're commonly parallel to the edge of the mineral, which is parallel to the lines, which is parallel to another edge, which is parallel to one of these stair steps. So all these things have to be aligned for there to be cleavage. Now, let me show you an example of something that has good cleavage with lines passing through it. So this is a translucent mineral, and you can see right now you've got a good hairline fracture running through it. Notice how straight it is. That hairline fracture is parallel to the edge, which is also parallel to this edge as well. So one good cleavage direction shown there. Okay. In some cases, the cleavage may be a little tricky to find, and that occurs when the mineral has a splintery habit. This particular mineral has such a habit, although I'm seeing good cleavage directions show up on this surface. Notice it's highly reflective, and you should be able to flip it over and you'll find it has a mirror surface on the back side that's also highly reflective, indicating that it is a cleavage direction. There's another grain and a surface here that's quite flat as well, indicating cleavage. Here's another one here. Oh wait, no, that's highly reflective, and there's some small stair steps. In this case, when you're looking at the mineral, you're going to want to use a magnifier to get up close and personal with it. Now, one thing to keep in mind is that you do have minerals like this that don't have cleavage. So this mineral has very flat surfaces, okay, and it has no stair steps, no real layers on it, nothing peeling off of here, no fractures passing through it. You can see that it's translucent. And so this mineral actually doesn't have any cleavage, and that can be a little bit tricky. What you're really looking at for this particular mineral is that it's a sort of a pyramid with a hexagonal six-sided surface, 1, 2, 3, 4, 5, and then the other one, 6 is over here on this side. You're looking at what we call the mineral's form or its habit, and this has an hexagonal habit. The habit is the external form of a mineral, and so I've sort of highlighted some of the differences, okay, between form here and cleavage here. So keep in mind these are important features for identifying and defining cleavage. You can have up to 6 cleavage planes in this particular set of minerals that you're looking at. Here are some examples of habit. Notice no stair steps, flat surfaces, no lines passing through that look straight and aligned with the edges, just flat surfaces up here and over here, right? All right, fracture, all minerals are fractured. They've been fractured from something else, but they're typically irregular fractures. We're looking for something, in this case, called conchoidal fracture. It is a series of smooth ridges and curved fractures that are not irregular. I mean, this is not perfectly smooth, but it is very smooth and sort of spoon-shaped. This is another one that you can see right here that's spoon-shaped in nature. That's called conchoidal fracture. Okay? And so it's best exhibited in minerals like obsidian, or sorry, rocks like obsidian. Okay? This property is called striations. Striations are grooves on the surface of the mineral, and we saw those in one of the first slides. You can see them here. They will not be aligned, so you'll notice that the grooves come along the surface, and then should be, if it was cleavage, you could trace it around. But now I'm cutting across these lines, so this is not a cleavage. This is striations, grooves or misalignments of the mineral surface as it's growing. It's growing little areas here first and less over there and more there, so it gets these little bumps or ridges. On this particular mineral, you can see the surface here and here. You can also see the little shadows there and there. Those are the layers of cleavage. So you have striations and then cutting across those, in this case, are cleavage. Okay. One of the things you're going to have to do for all of these samples is to evaluate the specific gravity of a mineral. Now, specific gravity is the density of a mineral, and density is mass divided by volume measured in grams per cubic centimeter. So here's your grams per cubic centimeter. It's going to be the density of the mineral divided by the density of water. Now, water is 1 gram per centimeter cubed. That's its density. So if we take grams per centimeter cubed divided by grams per centimeter cubed, it's equal to nothing. All of nothing, I'm just putting an X there because all of these units in this situation cancel and that cancels. So what happens when you take a mineral that's got a 5.5 grams per cubic centimeter divided by 1? Okay, you get a statement that you can read that this particular mineral is just 5.5 times as dense as water. Okay? For our purposes here, all I need you to do is heft 2 minerals and compare them. Okay? You're gonna group minerals into either low specific gravity or high. We can measure them in a straightforward way using some tools, but for our purposes today, we're not going to do that. And if I back out of this, oops, there we go. Discard some of those notes and come over to our document camera. All you're going to do is you're going to heft the minerals and note which one feels a little bit heavier. So typically those high specific, this is not always the case, typically those high specific gravity minerals are ones that are metallic. So I'm comparing this mineral here, which is about the same size, a little bit bigger than one of these other minerals like calcite. Okay? And I find that calcite feels actually lighter, even though it's bigger, and this feels a little bit heavier, even though it's smaller. So the one on the right is relatively high specific gravity. In fact, I could double its size almost. And the one on the left is relatively low specific gravity. All right, reactivity. Minerals, some of them at least, will react with hydrochloric acid. You don't have any acid probably available to you. All I'm going to do now is show you, though, what the reaction is like, and I'll provide you some insight later on as we move through the process as to which minerals should react and which numbers react. If I just put a drop on our sample here and zoom in on it, you can see here it's kind of shimmering and bubbling. I'll put one more drop. You don't need very much at all. One more drop there. Can you see it bubbling and shimmering here? See those bubbles forming? That's the mineral dissolving and giving off CO2 gas and creating a little solution of H2O and calcium dissolved in it. Okay? Minerals that don't react are going to do nothing. So let's pick one that does not react, and you'll just see that HCl, it's a very dilute concentration, just sits there like a little bump on the mineral. It's sitting right there. Okay? No reaction, no bubbles. The reaction will be immediate. So go ahead and dab that off, clean things up. Make sure you keep everything free of acid so other people can touch and examine the minerals, okay, without getting acid on them. All right. Back to the PowerPoint. We're getting close to finishing and wrapping up, so you've made some good progress here. The useful property for opaque minerals and metallic minerals that we're going to see is what we call the mineral streak. And the streak is the color of the mineral when it's been powdered. We're going to use a tool to powder that mineral. In this case, it's an unglazed tile that's been fired, so it's quite hard. It has a hardness of around 5 or so. And if we take a look at our picture here, we can see the mineral here on the right is being rubbed onto the streak plate, and this little powdered patch is what we're interested in creating for some of our samples. For many samples that are soft and light colored, this patch is just going to be powdered white stuff. Sometimes we use a dark streak plate, a black colored streak plate, to see what the color of the streak is. But I will just say out loud that you don't need this, because most of the minerals that we're really interested in streaking are those that are opaque and metallic in nature, and they will streak just fine on one of these white streak plates. So I'll take this mineral. Notice it's metallic in luster. It's 3 cleavages at 90 degrees. Rub my mineral there, and it made that little mark. Okay. Here's another one. This one will be fainter, subtle. You may have to look quite close if it's not leaving a dense patch of color. This particular mineral is diagnostic. It's a very pale yellow color that it's leaving behind there. Now you can subtly see that pale yellow color. So that's streak. Other properties that might be relevant. Taste is good, although I don't think you should taste the minerals. And I'll tell you that salt tastes salty, and I can help you out with this potentially later on. Another property that we like, it's almost diagnostic of certain minerals, is magnetism. And so if you have a magnet, you'll find that some minerals simply are magnetic. Now, really, in our box, only one is. So notice I have 2 metallic minerals here, but not all of the metallic minerals are going to be magnetic. So this one is not magnetic. As you can see, the magnet won't stick to it. So it is actually diagnostic of a mineral being present in your sample, and that mineral is called magnetite. Okay, so basically we're almost done here. Here are some of these other properties we're interested in. Magnetism, taste, okay? Minerals that smell, minerals that are flexible, and minerals that feel smooth, soapy, or greasy. So now you're confronted with this situation of you have all of these properties, you're learning how to identify them, and you're confronted with a lot of minerals all at once. You're going to have multiple tables, and those tables are going to list the various properties. They sometimes come in different arrangements. So I have something that's slightly different than your actual lab book, probably, depending on the class that you're taking from me. And you'll notice, though, that at the top, for instance, of the table on the left-hand side, we have metallic minerals. So for group 1, we're using luster to break out the minerals into groups. The next observation that you will make for these metallic, if you have a metallic mineral, will be the hardness. Is it harder than 2.5, softer than 2.5, harder than 5.5? Okay? And then the next property you'll use is the streak. So that means by this time, let's say you found it's metallic, it's harder than 5.5, you're up in this box. Now you have 3 different streaks which are fairly diagnostic, gray to black, greenish black, and reddish brown. And let's say you had magnetite, well, you'd also know that it's magnetic as well, and so that would lead you to this name here. Alternatively, maybe you don't have a metallic mineral. Maybe your mineral is a non-metallic mineral, and in this particular table you're using dark colors. So we have a dark colored mineral that might be black or green, okay, or even red. We're going to test hardness, and let's say that hardness comes out to be something like 2.5 to 5.5. So now we have a dark mineral, non-metallic luster, hardness of 2.5 to 5.5, and then the question is, what is the cleavage? If cleavage is present, that winnows it down to 2 options. So you don't even really need to be really awesome at identifying cleavage, mostly just noting that it's there, okay, rather than identifying all of the directions and their angular relationships. So now we have a mineral that's dark black to brown. It's got one perfect cleavage, which is very easy to identify, or we have a mineral that has a smell like sulfur, it has a light brown streak, and it has 6 good cleavage directions that you could find. So either one, depending on what you had, if we had just one cleavage, we'd be in this zone here for biotite. Okay, so that's how you use that chart. And we have one more chart for light colored minerals. Okay, you're going to fill in something that looks like this, your data sheet. So for each of these, luster, hardness, color, streak, those are all properties that you know of. Cleavage, you want to give the number and the direction and the angle, so be as precise as possible. And then you'll have other properties. Other properties could be reactivity, magnetism, smell, the flexibility of the mineral. Okay, all of those are other properties. And then you'll give the mineral name. And in this case, you may or may not need to look up the economic use. So this would be something you couldn't intuit. You would want to look up whether it was economic. If it's not economic, if it doesn't produce an element like copper or iron that we're using as a commodity to trade and bind to make products, then it simply is going to be a rock-forming mineral, which means that it tells us something about the history of the rock, but it's nothing anyone wants to buy. So this really concludes our discussion of mineral identification, the steps and the tools that you're going to need. You'll both need your mineral kit and your set of tools. The only thing you really won't have access to will be a dilute bottle of HCl, but I'll provide some information about that. And that's about it for identifying minerals. Make sure if you do get to the end of your table and you're looking at maybe one or two different options, that you see and review all of the different possibilities that I've put as short videos. I've identified most of the minerals that you will probably see in this kit, or at either of the libraries that you've gone to look at the minerals and to look at the rocks. And that means that you should be able to come up with a name. Once you get close, you can pick one or two videos and take a look and see what you think you have. All right. So till next time, I'll talk to you later.